Let's consider a data structure with a particular set of requirements. It has to be able to be traversed in sorted order reasonably quickly. It has to be able to insert and remove elements reasonably quickly. And it has to be fast to search for a particular element. The most intuitive solution one might immediately come up with is to have a linked list which is sorted upon insertion. What I mean by this is that when you modify the add step of this linked list, instead of inserting to the start or the end of the list, you traverse to the right place in the list and you insert there. For example, we have a linked list of integers which goes 1, 2, 4, 5, 6. We need to insert the number 3. We go 1 is too small, 2 is too small, 4 is too big, that's where 3 goes, before the 4 and after the 2. Makes sense? It's sorted at all times, we always have it sorted. To search, we just traverse through until we find the right number, because it's sorted. We know that if it's if it's going to be larger than the first number, it's going to be further along the list. If the number is larger in the list and it's not there, it could work, but it doesn't seem that fast once it gets really big. Let's take 1,000 length. We have to search quite far through that 1,000 length list to get anywhere. And that might not be optimal. Maybe there's something more efficient we could do. This is when we have to consider the use of our references, our pointers in these nodes, and what we could do with them. Do we just have to have one, or can we have multiple? And can we make some rules about where these pointers point to, which will help us in this endeavor? Well, what if we made our rules such that they helped us traverse this list in the most optimal possible way? And what if we just had a more helpful number of these references? Let's say that our nodes can point to 2 items. And let's make the rule that one of the items is less and one of the items is greater. You'll see very quickly how this can be useful. Let's start off with just one node at the top here. This node will have a value of 5. And let's say that the left node is less and the right node is bigger. So since the left node is less, we want to insert 3. We start with 5. 3 is less than 5, it goes to the left. Make sense? Simple. If the right is larger and we want to insert something to the right, let's say we're inserting 7, and now we have 7 to the right. So it goes 5 and then 7 if you try to find the largest element. To find the largest, you just go right, 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 right. Find the smallest, you just go left, 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 left. It's quite simple to find the largest and the smallest. But you might be wondering, what if I have a number that's larger than 5, but smaller than 7? It has to go to the right of 5, but then what does it do? Well, keep in mind that this is a recursive sort of data structure. Every node has these 2 references. So we go 5, well, 6 is larger than 5, goes to the right. 6 is smaller than 7, so it has to go to the left of 7. So it goes 5, 7, and then to the left of 7 is 6. But now you might be wondering how we can make a useful traversal out of this. How do we get this into sorted order? Well, the sorted order question actually becomes a lot simpler if we consider how our recursion is done. We can traverse the list. It's not actually a list, it's nonlinear anymore. We can't really call it a list. We can traverse our nonlinear data structure, our tree, in such a way that we get into sort order by going left, center, right, or right, center, left. The way we can do this is we can follow through. Let's say we want to go largest to smallest, because that's where our tree right now is a little bit more complicated. It's a bit of a better example. We go to the rightmost, rightmost, rightmost node to get the largest for the start. And then what is the second largest? Well, the second largest is going to be what was the center of the subtree that the largest is in. What does that mean? Well, remember, this data structure is recursive, so every node can be considered the root of its own subtree. Let's visualize the subtree of just the system with the largest node. That subtree has its center node, its lesser node, and its greater node. But what do we know about this subtree? We know that every one of the nodes in this subtree is greater than the nodes above it, because it was on the right of the node above it. So we know that it must have been larger. Since we know that it must have been larger, we can say that it is indeed all larger. We just have to traverse this subtree in order. And to traverse this subtree in order, we go furthest to the right, then we go to the center, then we go to the left. And remember, when I say in order, I mean largest to smallest. So right, center, left is the in-order version of that subtree. And then we go through every other one of the subtrees, and we go right, center, left, right, center, left, right, center, left, until we get through the whole tree and we get it in the correct order. We go left, center, right. If we want the opposite order of that. So if we want smallest to largest, we just go all the way to the left to get the smallest, and center then right, left, center, right, left, center, right, left, center, right, and we get the smallest to the largest. How do we search? Well, at every step, we simply ask ourselves the question: is the one we're searching for less than or greater than the current node? So if we want to have another binary tree, let's say this one has a root of 0. And then, well, we know that negatives are going to be on one side and positives on the other. That way we can say, is our number negative or positive for the start? And let's say on one side we got -5, on the other side we got +5. Right? That's what our tree looks like right now. And I'm deliberately only telling us about the nodes we can see. We can only see the root, the left, and the right. That's all we need to see. Because we don't care about what's on the rest of the tree. That could be really large, really small. We don't care. We just care about what we're searching for. And let's say the number we're searching for is -3. So we go 0. Is it -3 positive or is it a negative? Well, it's a negative. So we can go, okay, it's towards the side of -5. But it's larger than -5. So it's got to be to the right of -5. So we go center, then we go left, then we go right. And what's the right of -5? Well, in this case, it was indeed -3. And then this sorting algorithm, the searching algorithm, can be applied across the board. To search through the tree, all we need to do is just ask ourselves, is it less than or greater than at every step? And if it's equal, that is a separate case, but it's not much different. We just have to set a condition that one of them also takes in the equal. So one of the sides is less than or equal to, one of the sides is greater than or equal to. So hopefully this made binary trees a little bit more clear and understandable for you guys. Hopefully. Hello. If there's any questions, I'm happy to answer right away. Otherwise, I can get into it for today. We're doing sort of a lightning round recap of some of the content for assignment 3. Not all of it yet. We're going to get to heaps and stuff next time. But a lot of people have said that they are not caught up yet on binary trees, binary search trees, that sort of stuff. And there's some additional content I want to cover, such as yet another explanation on how to add your own speed tester methods, as well as generally the concepts that are going to be the basis of what we're going to do with heaps. So here I've got my tutorial project. I sent a link to it to the chat, but I can send it again in case there's any other joiners. And you can let me know if you've cloned that. In the meantime, I'm happy to answer any questions. And yeah, ready to get going. Today we'll be going over a number of things. First thing I want to go over is just the concept of the binary search tree. That's going to go over some of the methods. I'm not going to re-implement them. I did that last tutorial, but I'm going to give you a lightning round review of how exactly it was done. If you're wondering more specifics, that's tutorial 10. I recommend the Thursday one. But while you clone, I will get into it. Okay, so what is a binary search tree? Well, a binary search tree is a type of binary tree which is designed to help us search for elements more easily. I've got a graphical version of one here, which I'm going to run, and I'm going to use it to help explain the concept. So here we have a node, which has a score of 163. I'm going to zoom into that for you. That's not how I zoom in. That's how I zoom in. So here I've got a node with a score of 163. Now if I add a node that's larger, that larger node, which is going to have a score of, let's say, 218, that larger one is going to go to the right of it. And if I add one that is smaller, it's going to go to the left of it. Now this property is very important because it works recursively too. So if I have one that's even smaller than 74, if I have one that's like 50, it's going to add to the left of 50. Now this could get confusing at times if, say, I add something like 98, which is both bigger than 74 and smaller than 163. If I add 98 to this, it's going to go like that recursively. It's just going to recurse down and add to the search tree over there like that, right? I cover this in the animation. I cover this in tutorial 10. So hopefully if that's not clear for you, then tutorial 10 and the animation are the places to go. Now I'm going to reset that. Transform, fit to screen. I said transform, fit to screen. Okay, so that's the concept of the binary search tree. Now, how do we implement a binary search tree? It's like a linked list. We keep track of the head. Here it's called root, because a tree has a root. I guess a list has a head, right? The size is an int. You just iterate the size depending on how many things are in your tree. It's useful to know how much stuff you have, right? Then these are the methods to get largest and smallest. Those don't matter. here's add. Add is a recursive method, so we've got the recursive version of add, and we've got the non-recursive. Let's go through the non-recursive first. What are our steps? Well, I'll even write them down for us here in the greatest IDE of all time. So, steps to add. Check if root is null. If root is null, make root. And I'll make this a bit more close up for you so you can actually read it. Give me a second here. All right, so here we've got if root is check if root is null. If root is null, make null. Else, go recursive. So now we have recursive add. Right, in the recursive add, it's going to be a very simple bit of pseudocode. We see if the element to be added is bigger. Try if the element added is bigger. If there is nothing to the left, add it to the left. If there is something to the left, go recursive add again, because if there's something to the left, we just add to the left subtree, right? Hello to anybody who just joined. I'm just going over the basics of a binary search tree right now to explain the pseudocode, and then I'll get into explaining the real code, which was written previously. I'm just doing a quick lightning round explanation, and if you need more detail, that's in tutorial 10 for binary search trees. I'm just giving you the lightning round right now. So if an element to add is bigger, if there's nothing to the left, add it to the left. If there's something to the left, go recursive again. Now, else if the element else, well, I don't actually say else if. Here's else if the element is smaller. If there is nothing to the right, add it to the right. And if there is something already to the right, you go recursive. Add again. Right? So does that make a bit of sense to everybody? So we're going to add to a binary search tree, we check if the root is null. If it's null, we add it there. If it's not null, we go recursive. And then we go through recursively. Our base case is when there's nothing to the left. So these are our base cases here. If I go into here, actually, I'll specify that this is our base case. So base case. And this is our base case as well. So we go through on recurse until we get to our base case, which is there's nothing to the left or nothing to the right, depending on where we're supposed to add it. That's the pseudocode of a recursive adding algorithm for a binary search tree. Now, if I go into the, here, let me go proper again on this. Transform, fit to screen. So now, if I go into my code, which might take me a second while I select my display capture and I make it larger. All right, so if I go into my code here, I've got my add method right here. And I wrote this before, tutorial 10, but I'll just go through the lines and explain it. So what I'm doing here is I'm doing check if the node is larger. And here, this tree follows lefty larger. That's just because it doesn't have to. Like, you can make your tree left be larger or right be larger. It just matters that one of the sides is consistently larger, right? Here we're going to say check if it's the base case. In the base case, adding is really easy. We literally add it. And feel free to interrupt me if you have any questions or if you're confused about something or missed some detail. And now, in the non-base case, we work towards the base case. Right, now the same logic applies to here, but I'm just going to say instead of larger, we check if it's smaller. So that's part of the else statement. Notice smaller. Now, again, we just simply, it's very symmetrical, this code. Like, we don't actually have to write a very different code for either side of the tree. It's quite symmetrical. And then in the base case, we literally just add it. And in the non-base case, we recurse to get to the base case. Right? That should be very clear. Adding to a binary search tree, very, very easy. This is like super easy tier stuff. And it's, yeah, all you have to do is do what the logic seems to make you want to do. If I'm going to show you with the visual tool once again, just to really hammer it home how it's supposed to work. And in the animation it's shown as well. But just in the visual tool, if I spam remove, and then I add. So right now the root is null. There's nothing there. What happens the first time you add when root is not, or when there's nothing there and root is null? Well, it just goes to the root, right? So now we have a node in the root. Now root is no longer null. So if I add a random cat here, it's going to go to the smaller node. It's going to go left because, well, this tree does left is smaller. Ours is lefty larger. This one is lefty smaller. No big deal. But it says the smaller one is to the left. That's following that rule. Now if I add one that's bigger, so if I add one that's, say, 170, it's going to add to the right. Now what happens if I add something that's in between the sizes? If it's smaller than 126 but bigger than 97, like say 122, well, that's going to go to the left of 126 and then recursively go to the right of 122 until it finds its spot. That's kind of how the binary search tree add works. This is the binary search tree visualizer that I made last semester for a similar assignment in last semester's Comp 250. You could probably make something similar to draw your binary search trees and your heaps here. All right, so that is adding to a binary search tree. Now I'm going to go into a few of the other essential bare minimum methods for the binary search tree. The next one I'm going to cover is going to be in-order traversals. This one is adding it to a stack, so you get a stack out of your binary tree, which is all of your stuff in order. You can also do a system out print line with your in-order traversal, whatever you want. The traversal is the same. What you do with it might be different. So how do we do an in-order traversal? Well, if you remember seeing the animation earlier on my courses or wherever, you'll remember that in-order traversals go left, center, right in the case of, well, depending on which lefty larger or righty larger, and depending on if in order means largest to smallest or smallest to largest. Those things are subjective. But it either goes left, center, right, or right, center, left. Now, why does it do that? If I open the visualizer again, I just don't know why I keep closing it. I should really just keep it open. But if I open the visualizer here, and I just add, let's spam add a bunch of stuff to it, maybe not that much stuff. Okay, it's going to take a second to spam remove now. Oh, it's taking forever. It's pretty bad. I'll just close that and open it again. Shouldn't have spammed add. That added like a ridiculous number of things to it. I'll add a smaller number of things to it, and I'll show you again why left, center, right is the way we do it, or right, center, left. So I'm going to add random, add random, add random, add random. Okay, so now we have this tree to traverse. Let's say we need to find this in order. How do we get it from smallest to largest? Well, we add to our stack left, center, right. So I'm even going to do it manually. I'm going to do a manual traversal here, and I'm going to show you what I'm talking about. Here I've got the world's best IDE on the side, that being Vim. And in Vim, I'm going to do this traversal. So I'm going to say traversal output. Right, and I'm going to go left, center, right. So first, left, what is the left of head? It's null. So I'm going to ignore the nulls. I'm not going to add the nulls to my traversal. So left was null, center was 13. Right? Now I go right. But when I go right, I do it recursively. I don't just go add the value of the right. Remember, it's left, center, right, not center, left, right. So I don't add the center. I add the left. What's to the left? Well, it's this 56. But I'm not going to add the 56. I'm going to add what's to the left of the 56. And what's that? It's 40. But I'm not going to add 40. I'm going to add 21 because I'm adding the leftmost thing. The leftmost thing here is null. Then I add the center of this subtree, which is 21. Right? Now I'm going to add the right of this subtree, which is null. There's nothing there. So I'm going to add null here. I'm not going to add the nulls just because that can get confusing. So remember, I went left, center, right, left, center, right. Then I went, left, and then that left went left, and that went left. And now I went center, which is 21. Now I have to go left, center, right again. So the center here is 40, and the right is null. So I added the left. Now I have to add the center, so that's 40. And the right is null. Now I go 56. 56 is the center, so I add that. We just added the left, which is 40. And what is right? It's 84. So now I add the 84. Now I go up again, and I add the center. The center was 139, so I add the center. Then I do the same thing with the right. I do 154, then right again, 204, right again, 216. And I skipped over the fact that this one you also add the left first. So if this one had a left, I would add the left, then the center, then the right. But since none of these have a left, I just added all the rights. And here it is, the traversal. And what do you notice about it? Well, it's in perfect sort order. It goes, 13, 21, 40, 56, 84. It's in increasing order. So do you guys see how I did that? Does that make sense? I went left, center, right, recursively until I got the full in-order traversal. Very nice, I like. All right, how do we do this in code? Well, it's very simple. If the right, well, here I'm doing in order is right, center, left because my tree is lefty larger. So here I'm going to specify right, center, left because this tree is lefty larger would be left, center, right if it was righty mighty, or however you want to call them, right? So this one is lefty larger, so it does the smaller one first. It checks if there is a smaller one, so check if there is a smaller subtree to the right. Recurse through the smaller subtree first. Then, base case there, or we hit the center. Center is a leaf. And that means we're going to add to our output. So we output here at center. Right, makes sense? Then here we're saying check if there is a larger subtree to the left. Recurse through larger subtree after. And then woot, we are done. Return the output. Very simple stuff. Hopefully you guys understood all of that. We go recurse through the smaller subtree, add everything, recurse through the larger subtree, return our stuff. Totally clear? Hope so. That is the in-order traversal of a binary tree. That is very similar to the reverse order traversal of a binary tree. The reverse order traversal is doing the same thing, except instead of going, if this one's going right, center, left, it'll go left, center, right. And if this one's going left, center, right, it'll go right, center, left. Otherwise, it's identical. You can tell because the code is literally copy-pasted. If you see tutorial 10, you can literally watch me copy-paste that code from in order to reverse order. And hello to our new joinee, where I'm just doing a lightning round recap of assignment 3 content. So right now I'm doing binary search trees, and I'm covering stuff like the insert or the in-order traversal, and that's all I've covered so far. Next stop will probably be the iterator, unless there's something. No, I'll do searching first. So the name of a binary search tree is a binary search tree. Why is it called a binary search tree? That's because we can search for stuff. I'll give you an example using this visualizer of how we can search for something. But first, let me add something as I'll add a few more nodes here, so the search is a bit less trivial. And maybe can you guys give me one of the numbers on this tree to find, to search for in the minimum number of steps, and I'll show you guys how I can search for it. So just give me one of the numbers of one of these nodes, and I will show you the searching algorithm. 84, perfect. Let's see. So all I have access to is the current node. We're going to start at the head. We're going to ask the question: is 82? It's 84, right? Oh no, is 84 larger than 13? Yes or no? Well, 84 is obviously larger than 13. So is it going to be to the left or is it going to be to the right? Well, here it's righty-mighty. The right one is bigger, so it's going to be to the right. Now, is 84 equal to 139? No, it's not. Is it greater than 139? No, it's not. It's less than 139, so it must be to the left. Now we ask the same question at 56. Is 84 less than 56 or bigger than 56? 84 is bigger than 56, so it has to be to the right. And here it is. There's 84. We found it because 84 equals 84. So does that make sense? What I'm doing is at every step, at every node, I'm asking myself the question: is the one I'm searching for bigger or smaller in terms of score? If it's bigger, it's going to be, in this case, to the right. And if it's smaller, it's going to be to the left. In our other example in the code, it's the left and right are swapped. That's just to show that it doesn't matter what you call it, left or right. We just remember we have a rule, and we're following that rule. And the rule we're following is it to the, if it's left larger, if it's right smaller, or if it's right larger, if it's left smaller. One of the sides is smaller, one is bigger. Left and right is the concept to help us visualize it. We just have 2 pointers, one to a bigger one to a smaller one. And that's how we find 84. Now, how do we code that? Well, here in our binary tree, we have find and find recursive. Why do I have here? Find recursive counter. Oh, this is so I could stop stack overflows from happening, I believe. I wanted it to cancel if it recurses too much. We're just going to pretend that isn't. Oh, I'm doing a system out print line as well. Okay, fine, I'll keep that. That was from showing you guys why we need a heap. That comes later in the lesson, but for now I'm just going to leave it to explaining the find method. So all we have to do is we have to return the one we found through the find recursive method. So this is just hiding the recursion. We're just passing the root and what we need to find. Starting at the root, what we do, we ignore this counter for now. This has nothing to do with the method. This is just for testing. In fact, I'll make it separate. So I'll just say this is useless and has nothing to do with anything. Right? Don't care about that. Now, if we say here, if the current is null, well, we return null because that means that the element doesn't exist. Why do I do that? Well, I say that if we reach a null node, then we can't traverse any further. We know that it doesn't exist, so we return null. If the data at the current node is the same as what we were looking for, well, we return the current node. Makes sense, right? Because if we're matching what we're looking for, then we found it. Now here is the fun part. We're checking. So if it's larger, it must be to the left. And here we're saying if it's not larger, must be to the right. And then we just repeat the finding algorithm that goes through. It does exactly the same thing I did manually. It just checks. Here you can actually see in the code where it does it. It says, is it bigger? So here, if we're finding 84, we say, is it bigger? Yes, we recurse down to the bigger side. Is it bigger? No, we recurse down to the smaller side. Is it bigger? Yes, we recurse down to the bigger side. Is it equal? Yes, we return it. Does that make sense? That's what the code is doing. It's doing the exact same thing I was doing manually. Very, very simple code. It works quite effectively. That is how we find an element in a binary tree. Next thing we're going to go over is the iterator. What is the iterator for? The iterator makes enhanced for loops possible. So if I wanted to do, let's say, for every dog in my dog tree, or for every Pokemon in my Pokemon tree, as I have here, what you all have to do is you have to implement the iterable interface up here, which is already done for you in the assignment, and that will give you the need for an iterator. Now, I have it done a little bit differently than your assignment does. Instead of having an inner class for the iterator, I have a anonymous class for the iterator. The effect is the same. We just have a class here, which is the iterator. And here, what the iterator does for me is very simple. This is maybe not the optimal iterator for some situations. If you're doing something like in your assignment, this may or may not be the best solution. I would say it's pretty good, but it might not be ideal because it does traverse the entire tree in order. So if you break, it's still going to have a high time complexity. This is not always optimal. It's pretty good, but it's not the theoretical best for some cases. What do I do? Well, first thing I do is I traverse the tree in a reverse order here. Because I'm using a stack. You know how when you pop from a stack, it reverses the order of whatever you put in? Because when you fill a stack, it goes first in, first out. So here, I do the reverse order traversal so I can get it into an order which the stack likes. Like it gets into the kind of order the stack is a fan of. So I can do a pop to make it go. Then what do I do? Well, the first thing I do is when the iterator gets created, I create this stack using a reverse order traversal, which is the same as our in order traversal. We save the stack. If it has next, well, that just asks if the stack is empty. And all that next does is next returns popping from the stack. That is the iterator. The iterator will iterate through the data set. When it's created, when you enter the for loop, it will create the stack for a reverse, or like using a reverse order traversal. It'll fill that stack up with everything in the sort order from the tree. And then it'll iterate through in order, basically giving you the sorted data set. So this can also be imagined as a ridiculously slow sorting algorithm. Now, I say ridiculously slow. Why do I say that? Well, I say it's ridiculously slow because it's not optimal yet. It's not a heap. A heap would be a more optimal version of this. But before I get into the theory about why we need heaps, I should probably give you guys yet another essential method. And that essential method is the delete method, to delete something from the binary tree. Never before seen yet, but don't worry, I'll do it right now. And I'll just code that right in front of you guys. This will be the slower part because I'm going to be introducing the code as I go. So it's going to be called, let's say, public void delete. Or you know what? I'm going to return a... should I return the one that I deleted? No, I'll be cruel today and I won't. Public void delete e data. And it's going to say that it's going to delete whatever data I pass to it. So it's going to delete the node with the data that I pass. And now I'm going to call delete data, comma head, and that's going to start a recursion. Now, wait, I need to say this dot head, probably. Do I call it head? No, I call it this dot root, of course. Now I have to create the method to do the recursion. It's going to be called private void. Now I have to return a tree node. Oh, private tree node e delete e data tree node e node. Right, now what do I do? Well, I say, base case, if the root is null, there's nothing to delete. So if node is null, return node. Right, don't care. I just return null if the node is null. Now I need to traverse the tree to find the right spot, because to delete something I still have to find where it is. So I'm going to say if e dot or if data dot compare to node dot get data greater than 0, node dot get left, or node dot set left, because I'm setting the left to be the new deleted subtree. So I'm going to say delete node dot get left and data. So now I need to explain this step, because this step might seem a little bit confusing, and it's actually the other order. It's data comma node get left. So this step might seem a little bit confusing. What exactly am I doing here? I'm setting the node to be the output of the delete method. What the hell is this? Well, consider delete returns null, right? If the node passed is null. Delete returns a subtree if it isn't null. Therefore, in the base case, this just sets the left to null. And in other cases, runs a recursive delete through the left subtree. Does that make sense? So this deletion method is a bit more clever than it's made out to be at first. It's actually like, also I'm hoping you guys are seeing it, are you? Don't have my video preview up right now. Oh, oops, you missed those comments there. Here you go. So I was saying that this call here, the set left to the deletion, is quite clever because it will return null and it'll set the left to be null if it's just deleting a leaf. So this takes care of deleting a leaf. Takes care of leaf deletion. A leaf being a node with no children. And it also takes care of subtree deletion recursively. It's a very clever little bit here, this method. Right, now else if, we're just going to go through the larger subtree now. Now, if they're less than, we say node dot set right, delete data node dot get right, and it's same recursion, exact same concept as above. Same concept as above. If you guys have any questions at all, feel free to interrupt and ask. Happy to answer. Now, of course, we have an else block as well, and this is if this is the one to delete. So if node dot get right. Well, no, actually, node dot get left. We're doing left first. So if node dot get left is null, what we gotta do is we gotta return node dot get right. And else if node dot get right is null, well, you guessed it, we return node dot get left. These are very, very symmetrical. Okay. Now what we do is we set the data of the root to be the value of the minimum node from root dot right. Now what does that mean? Well, could you explain those last two again? Okay, so this is actually setting up for the recursive delete. We're saying that if the left of the node is null, all we're going to do is we're going to replace the node that we deleted with the right of this node. So if we are replacing a node right, above, that is in the lines above, 201 and 204, we can replace the nodes directly by swapping this node in, but only if it has a child on one side. Now, how do I explain this better? Maybe I'll show you in the visualizer, because it's kind of maybe hard to understand as a concept in general. But what if I want to remove the one with 21? What can I do? Or actually, you know what? Maybe I'll remove the one with 40. That could be a better example. So let's find the one with 40 and remove it. What happens? Well, this subtree shifts up. See, the 21 and 25 subtree shifted up to replace it. That's what this code is doing. It's shifting up the subtree if there's only one child. Hopefully that makes it more understandable. Now I'll go into the last bit of the thing. So now in the other cases, we want the node's data. We're going to do a bit of a weird move here, but you'll understand it soon. So set data, and now we're going to find the smallest. Oh, but I don't actually have a method right now, which gets the minimum node given a subtree. So we need that. We need the smallest node in a subtree. Let's create that method right now. We're going to call it, private e smallest in subtree, tree node e node. Now this will just give us the smallest item in a subtree. So e minimum is equal to node.getData. Now while node.getLeft is not null, minimum equals node.getLeft, or node.get left dot get data, and node is equal to node dot get left. So this and this is actually going to be a bit of a hint to what's coming later, because of how this traversal can sometimes be slow. But now we're going to set the data to be smallest in subtree node, right? Now we're going to say node dot set right, delete node dot get right, node dot get data. I did those in the wrong order. I always do the wrong order here for some reason. But here. So what is this doing? Well, let me explain. So we're going to go through here in the case of a big subtree, and we're going to say we're going to set the data to be the smallest in the subtree. So the smallest, oh, oops, I forgot a step. There we go. That's going to be much better. So we're going to set the data to be the smallest in the subtree of the biggest. So what does that mean? Well, we set the data in the current node to be the, oh, this should all be in this. Is this else block closed properly? No, it's not. Oopsies. There we go. And now here, now I'll finish up the method. But here, we set the data in the current node to be the smallest from the subtree of biggest. Now, what does that mean in terms of the visualizer? Well, in here, we have this tree. Let's say I want to delete from 56. Maybe 56 will do this, right? What is the easiest replacement for 56? Well, it needs to meet two qualities. It has to be bigger than 21, and it has to be smaller than 84, right? Does that make sense? The item that's going to be in this place needs to follow the rules of the binary search tree. So it needs to still be smaller than 84 and bigger than 21. So what node meets the requirements of being smaller than 20 or smaller than 84 and bigger than 21? Well, it would be the one that's bigger than 56, or yeah, it's bigger than 21, so it'll be on this side, and it's smaller than 84, so it's going to be on this side. That's why it's the smallest one from the subtree of the biggest one. So here's going to be 82. So if I remove 56, well, actually this one is doing it from the smallest. So this one subbed in the smallest, or the biggest from the smallest subtree, but you can also do smallest from the biggest subtree. Does that make sense? you're taking the one that meets the conditions, which is either the smallest one from the biggest subtree or the biggest one from the smaller subtree. And then that will meet all the same conditions as the node you replaced. And then you go through and you delete the repetition. So this will become a base case because before you found the minimum, so you found a base case. That will be really easy to remove, right? So this way we're basically cheating the system. We cheat the system here, and we remove using the base case. Here, we cheat the system, and we remove using the base case. We swap our node for one that meets the same requirements, bigger than one side, smaller than other. We delete a leaf, which is now a duplicate. Right, and this covers now all the cases for deletion. And this is how we delete something from our subtree. The delete method is by far the most confusing and the hardest method of a binary search tree. And it gets even harder when you combine it with a heap. But this will hopefully make the concept make sense. Notice the concept of fixing what we screwed up. We took a risky step here, a risky step to get to a base case that we're not sure if it's going to work out. And then we did a move to fix the problems we made. So this here, a risky step that messes up our tree, but makes removing easy. And this is a step which fixes what we messed up. Right? Makes sense? That's removal. Now, to convince ourselves that removal is actually working properly, we can write a quick test for removal. We're just going to add that to our main method. I'm going to add it before test binary tree. So I'm going to say binary tree, and we're going to store integers in it. New binary tree. Now we're going to say, let's say, binary tree dot, what do they call it? Tree. Okay, I'm just going to do some now. I'm going to say tree dot add 50. Now I'm going to copy paste this. Let me just change the numbers. Yeah. 50, 50, 50. Now I'm going to add like a bunch of different ones. So 50, 30, 20, 40, 70, 60, 80, and I'll do 55 as my last one. And now I'm going to say tree.delete. Let's say I want to delete, first I'll delete the root, see if that worked, then I'll tree.delete one of the edges, one of the leaves, and that will be 80. And then I'll delete one of the ones around the middle, which will be like, let's say, 30. And we're going to use the debugger to see how all this runs. So I'm going to hit it with the debugger. Now I'm going to change my view so you guys can actually see everything. Let me just do that really quick. Sorry, I've been really zoomed in this whole time. I kind of forgot. Now this just needs to be reset. So transform, fit to screen. So here we have the debugger with the tree. What does the tree have? It has a size of 7. Oops, I forgot a crucial step. I forgot to reduce the size when we delete something. Let's just do that right now. Where do we size minus minus? Well, we could size minus minus when we have returns. Do we? Well, no, these returns will happen otherwise. So we actually have to be clever about our size minus minus. It'll be here. I don't know if that's even going to work every time here. The size minus minus thing, Will's probably not going to properly keep track of it, so I'll make a to-do. Proper size tracking. I can't be bothered right now. I'll just leave it as a to-do. That's something I forgot to do, but we'll just we'll debug it anyways, and we'll see if the deletion actually does its job. So our tree here has a size of 7. I'm going to go over step over. So now notice that our root has 50. And we have which children? Well, we have 70 on one side and 30 on the other. We're going to step over deletion. Watch it happen. So now our size is 7. And notice how our root is now 40. So our tree got swapped up. Our 50 got swapped with the subtree from 40. What does that look like in the visualizer? Well, If we delete our root here, which is 13, it's just going to shift one of the subtrees up. Here, shift the smaller subtree up to go there. Now, if I delete, let's say, 139, which is the root of that subtree there, see, notice how 139 has its own subtree. If I even draw subtrees here, here's the subtree of 139. You can see it right here. If I delete 139, what's going to happen to that subtree? Well, it swaps up the biggest of the smallest of this one, moves it up the tree, right? That's always what happens with removal in the middle. Now, if we skip forward one more step, let's find 30. 30 is in here. Oh, no, it's going to delete 80 first. So 80 is to the left of that. And 80 is a leaf node. So let's see what happens when we delete 80. Is 80 still there? No, let's just make sure that it actually stepped over properly. So 70, right is 60, left is 80. Oh, that appears to still be there. That is a glitch. Why is it not deleting 80 properly? Let's see. We're going to debugger it again. This is now a debuggering tutorial. We're going to step over, step into. This will get into the method where it's trying to delete it. Step into again. Here's where we're deleting 80. So what are we trying to delete? Data 80. We're at the head right now, right? Yeah, so we have to go left, left, and then we get to the node we want. So let's see. That is 80, this is that, so we step in here. Why does it not go properly? If compare to, no, that's at left, get left. And just have to go back a step here. Give me a second. Is there any way I could zoom in just a little bit, please? Yeah, sure. I'm just testing to see why my remove is glitching out all mean for 80. So I'll zoom into where I'm viewing here. I wasn't sure which part to zoom into because I was looking at multiple parts of the screen, but I'll zoom in comme ça. So now hopefully you can see a bit of the debugger and which line I'm running right now. So I'm going to go through with the debugger. I'm going to check delete on 80, step in, step into this deletion 2. The node is not null. Which node are we at right now? We're at the head. We go through, we check if the data is to the left. Is it to the left? Yes, it's definitely going to be to the left. So this should step into this. Ooh, no, it didn't. It went to the right. That's our problem. We're doing the wrong comparison here, I think. We need to go like this. We're going to swap our order here. I think that's what's going on. So now I'm just going to make sure. I'm going to rerun it. I'm going to see if that fixed it, that bracket order. Bracket order is probably the most common issue with this kind of thing. Now we're going to see. Right now our tree has a root of 40. Then it has a left left of 80. We remove 80, what happens? Its left left is now null. Okay, so we figured out the problem. It was indeed that my brackets were the wrong order. That's a super common problem with every method in a binary tree. I'm telling you guys, if you have problems, that's the first thing you should check. It's these bloody things. When I was writing these in class, this was the exact same problem I faced every time. It's not like it's the most common problem by a little bit. It is probably the most common problem by the largest margin you could ever imagine. Like it's 80% of the problems we have with these. At least in my experience, that's what it's been. It's these bloody comparisons. Just make sure you do them all correctly, and you'll save a lot of effort for yourself. And hold on, I'm just going to crank my ISO so I'm not so bloody dark. Yeah, changing camera settings. Got to make sure it's all cinematic, you know. No, that's the wrong way. Ooh, hello, hello, slow shutter speeds. Anyways, enough of my camera nonsense. I'm all spooky and slow shutter speed now because I have no lights on and I'm in dark theme. Anyways. So what do we have here? We've done remove. Have we done iterator, guys? Just asking you guys so I can see if I remember what I did. Because I don't remember if I covered iterator yet. I think I did, right? I'm going to say I did. You can correct me if I'm wrong. Okay, so that's all the main methods of a binary search tree. We'll get to heaps next episode, but right now I need to show you the basis of why we care about heaps. Why are heaps even a thing? Why would we ever want a heap? Why would we ever want in focus? So let me tell you about some situations in a binary tree that suck. Let's create a new binary tree here. I'm going to add a cat to it. It's going to just be a random one. 158. Now let's say all of our cats happen to already be sorted. They're already in order, and the order they're in is largest to smallest. Now, can I make it even smaller? What do we see here in this binary tree? What does it look like? Well, it looks a little bit like a linked list, right? Does this look, it looks familiar to you if you've seen these singly linked lists before. Now we know that singly linked lists suck. They're really slow to traverse. Now let's look at how our method works for finding the smallest. It says, while the right is not null, temp equals temp.right, return temp.getData. Well, what does that look like? It looks like a linked list traversal. It looks like I'm going to the end of the linked list, right? Now how does that run? It runs an O of n in this case. O of n for the number of things in the tree. That's pretty terrible. We don't want our stuff running in O of n. That's the core basis of what a heap is. This is the idea of balance in a binary tree. This tree is maximally unbalanced because every node has one child, right? This is what we want to avoid. Does that make sense? This is the worst case. Now, I'm actually going to demonstrate why this is what we want to avoid by helping you guys with writing speed tester methods. So, there's no speed tester provided this assignment, but you can use the one from last time. You just have to write your own tests. That's what I'm going to be showing you how to do today. So, how do you write a speed tester test? Well, first, declare your method. Here I pre-declared them, but you don't have to. You have to put @benchmark at the top, and it has to be in like one of these classes. It has to have some lines of code. There's a full text guide up above. But basically, you have to have a main method which calls visualizer.launch with its class name. This line has to be in your main method. You have to have the runtime tester imported, which is same as assignment 2. And you have to declare your methods like this. First, tag them with @benchmark at the top, and you have to give them a name. So you have to type name equals and then whatever you want to put. Here I put iterator, and then optionally you can add a category. The category just puts them all together so they're easy to find. Here I put the category binary tree. Now how do we do this? First thing we do is that we fill our binary tree, and then we can run methods on it. So here I built a method already to fill our binary tree, and I built numerous actually. I built unbalanced, unbalanced, and balanced. These are to show the speed differences between balanced and unbalanced binary trees. So let's get to it. I will first write the iterator test. I'll say binary tree. What is it? String? Yeah, string test subject equals build balanced binary tree. It doesn't have to be balanced for this. For iterator, it actually doesn't make a difference if it's balanced or not. Maybe I should demonstrate that. I'll do an unbalanced version too. And then all I'm going to say is long start time is equal to system.nanotime. That takes the current time in nanoseconds. Then I'll do for string in test subject, which calls the iterator. As you know, the iterator just helps with enhanced for loops. So all this is doing is it's iterating through the subtree there. And then I'll say long end time is equal to system.nanotime as well. Nanotime. Oh, I forgot to give the string a name, so for string, yes. Right? And then I'll say return end time minus start time. So what is this doing? Well, this is taking it's creating a tree outside of the test, so we already have one of the right size. It's taking the time when you start, you're doing your operation. It's taking the time when you finish your operation, and it's returning the difference. Does that make sense? A very simple procedure here. That's how you write a speed tester test. That's all you have to do to know how fast your iterator is running. Just like that. Now to show you like the unbalanced version, just to prove that iterator is the same speed if it's balanced or not, I'll call it unbalanced iterator. And instead of, and it's going to be called test. It doesn't actually matter what your method name is, it's never used. And here I say build unbalanced binary tree of size input and do that. So now if I run my sorting algorithms drag race speed tester here, I've got all these graphs up. That's because I have a lot of various stuff here. I've got all these methods, I've got assignment 2, I got everything, right? I'm just going to reset that. I'm just going to only use the binary tree. Unbalanced iterator and let's call it balanced iterator. So here's our balanced versus our unbalanced iterator. They shouldn't have much of a speed difference at all in terms of time complexity, do they? No, not really. You can see up here, well, one of them actually started to stack overflow. So that's one problem with binary trees in this tester, is that they can stack overflow rather quickly. at times because of how recursive they are. And when it's unbalanced, Stack Overflows are very easy to happen because it has to recur so many times, right? Like for a given data set. We want iterator and unbalanced iterator. But in general, iterator and unbalanced iterator take about the same amount of speed. Right? Does that make sense to everybody? They're about the same speed because iterator runs in O of n. It goes through every element of the tree. What does iterator do? It does left, center, right, center, left. So no matter how your tree is shaped, it'll take the same amount of time. But can you guess how fast add node is going to go in an unbalanced tree? How long will it take to add the biggest node to this tree? Like how long would it take to add a node of score 1000 to this tree that's on the screen right now? Now notice the tree has nothing on the bigger side. The bigger side is totally empty. It only has stuff on the smaller side, right? So to add to the bigger side would be O of 1. But how would it be to add to the smaller side? Well, the smaller side has every element. So it would actually be O of n to add the new smallest and O of 1 to add the new biggest. That's the upper and lower bound to our runtime efficiency. Let's demonstrate that. So we add a node to a balanced tree. Let's say unbalanced left and add node unbalanced right. These are going to be my two options. So let's just add node first. Right, so add node, how do we do it? Well, we say, I'll copy paste most of it actually because it's very similar. I'm just going to take this. And now instead of making it traverse the list, instead what I'm going to do is I'm going to say, string test subject is equal to, and then I'll just copy paste my random string generator here from before. Now remember, this is adding it to a balanced tree, or just subject 2, I guess. And now I'm just going to say test subject dot add test subject 2, and that's going to add my string to my binary tree here, and plus I. I'm just going to say plus input plus 1. Okay, so now this is just going to add to my balanced binary tree. How do I do the unbalanced version? Well, first I just copy paste this. And now I'm just going to say, no, this is build balanced tree. Now here I'm going to say build unbalanced tree, decreasing. And the subject I'm going to add will just be character value 0, so it's going to be the smallest every time. So maybe string dot value of that. And now I'm going to add the same test subject 2, but instead of doing the left unbalanced, I'll do the right unbalanced. So build unbalanced increasing. And we're going to compare the runtimes of these various things. So if I run sorting algorithms now, we're going to reset. I'm only going to add the ones we care about. So that's going to be, just let me fill the screen with this. So now I'm going to add unbalanced left, unbalanced right, and add node. Now we can see they're all similar at the start, but we're going to see one of the unbalanced ones is going to start taking off, especially if I increase my steps per iteration. What do we notice here? We notice that unbalanced right or unbalanced left is spiking up. It's the least optimal case. Add node unbalanced right is kind of bad. Well, actually, no, it's not kind of bad. It's kind of all right. Add node is also kind of all right. But do you see what happens to the runtime efficiency when our tree is unbalanced with a bad direction, when we're adding something that's the smallest, for example, to the tree in this example? Do you see how that really screws up our runtime efficiency, right? It screws up our runtime efficiency to have the messed up tree, the one that has a lot of children with no other children, the one that's unbalanced. This just Stack Overflowed. That's another problem with that, because you have so much recursion going on that you're going to Stack Overflow. Because you're going next so many times, it'll even Stack Overflow quickly if you have so many unbalanced nodes on a tree, right? So what are the two problems with an unbalanced tree? Crappy runtime efficiency on methods like add and traverse, right? And it's going to be crappy because it's going to Stack Overflow. How do we avoid these unbalanced trees? That is the heap. That is what it's for in this situation. And the heap adds more rules besides just left is larger, right is smaller. The rules the heap adds are that every subtree must be complete. So you cannot have a node with no children unless it's at the very bottom layer. That's one rule of the heap, which guarantees that you won't have these cases where it just runs off to the side, right? And that's the first big thing of the heap. So I'll give you a few examples and I'll tell you heap or no heap. So if I spam add, is this a heap or not a heap? It's not a heap because you can see here that there are nodes without both children on these upper layers, right? So on this layer, there is a node with no child on one side. It's not a heap. Why is this not a heap? Well, the heap's point is to reduce the number of these unbalanced trees. Not really. There's other points to the heap as well. For example, the heap has a rule that the biggest one must always be on the top if it's a max heap, or the smallest one must always be on the top if it's a min heap. Those allow you to access the smallest to the largest in O of 1. But those are not the point I'm trying to hammer home right now. The other property is that it must be complete, right? So this one is not a heap. Okay, I'll restart it now, and I'll maybe give you one that might be a heap, and maybe you can actually tell me whether or not it is a heap. So where is it? It's over here. No? Here it is. I'm going to run that again. And I'll introduce the actual code of a heap next time. So this is a heap or not? Actually, it's not on the screen. Is this a heap or no? Yeah, it's not a heap because it has nodes here which don't have children. If it was a heap, this one would have to have a child here, and one here, and one here, and one here. How do I make it into a heap? Let's turn it into a heap right now. I have to have one that's smaller than 80 here, so I'm going to put 76. I have to have one smaller than that, so I'm going to put it at 50. I have to have one bigger than 50, but smaller than 76, so I'll have one here at 74. Oopsies, that's wrong. Let's remove 74. I have to have one, yeah, that's bigger than 76, but smaller than 88. That's more like it. So that would be like 77. Right? And I also have to have one that's smaller than 132 and bigger than 88. So that would be maybe a 122. Right? And now this is a heap, right? Because every node has full children. Now here's another question. Is this still a heap now that it has that? Now your intuition might say no, right? Because there's a node without children. But this actually still is a heap, because the point of a heap is you have to add them left to right. So a heap is a node where is a tree where everything is complete like this, but you add the children from the left to the right. Why do we care? Well, a heap actually has another generalization we can do. A heap lets us condense it into an array. How do we mean that? Well, imagine this. You have a tree that follows this rule. Imagine you squish it down so that index 0 is the root, index 1 is root.left, index 2 is root.right, and then you recursively follow that through for the subtrees. If you follow the heap rule, you'll have no gaps in that array, and that lets you access one of the indices in O of 1. That is one of the big advantages of the heap, is that you can store it in an array. Now, if I add one here with a value of, let's say, 55, this is still a heap, right? Because they're still going left to right. So yeah, still a heap, right? Now how do I make it not a heap? Well, if I add a really big one, like 242, this is not a heap anymore. But that raises the question, how do we add 242 to this heap? Actually, what we have to do is we have to add it to the correct spot, and we have to bubble it up to where it's supposed to go. Kind of like bubble sort, but not that bad. Where we bubble it up to where it's supposed to be, keeping in mind that in a maximum heap, the biggest value has to be at the very top, right? So, that is the properties of a heap. The biggest has to be at the top in a max heap. The smallest has to be at the top in a min heap. And this is still technically a heap, but it's not a min or a max heap. And this is not a heap anymore because the 242 is here. But if I remove the 242, now it's a heap. Hopefully that's clear to everybody. This has covered assignment 3 content on binary search trees, on the introduction to the concept of the heap, and on iterator. And that's almost enough to get your assignment going. The only thing you still need is the implementation of the heap. That's next tutorial. Any questions? Floor is open to you. Otherwise, we'll be wrapping up. All right, awesome. Yeah, I'll keep it up, keep running for any more questions that anybody might have. But besides that, well, if you don't have any questions, you're good to go, and good luck on assignment 3. Heap content is covered next tutorial, and make sure that, oh, also, little note, you're welcome to share your speed tester step definitions with anybody. If you use a speed tester for your thing, or if you make a tester kind of like the one I have on screen here, you're encouraged to share that with your classmates. It's a great way to get ahead in the class, to make lots of friends, and to be noticed by the teaching staff. It's a really fantastic thing to do. Highly recommend it. All right. Good day, guys. Enjoy. Fare thee well. If you have any questions you didn't think of now, you're welcome to ask them on Piazza or wherever. Farewell.